So, efficiency. Now, talking about mechanical efficiency first. When we talk about mechanical efficiency, it's a pretty simple equation. Okay? You can measure the work in and you can measure the work out, and that gives you your efficiency. That gives you a ratio. So that ratio, whatever it may be, you multiply that by 100% and you get the efficiency percentage. Okay, the efficiency number is going to be like 0.5, 0.7, point whatever. But it's simpler to talk about efficiency as saying 70% efficient, 20% efficient, 12% efficient. Okay, so that's the general definition of efficiency. The work out divided by the work in. If you're talking about it in a thermal system, the efficiency is being expressed as the work out divided by heat in. The thermal energy that's being delivered in times 100 will give me my percentage of efficiency. 20%, 30%, 40%. Now, this is just a story, a little sidebar, just to make this video a little more interesting. I had a friend that used to work as a mechanical engineer, and he used to work for Honda, building power plants. Not power plants as in fact huge colossal buildings, but more like electrical generators. The word power plant is just describing something that can produce power, usually gas power and stuff like that. And he was telling me that Honda had developed an engine that was 100% efficient. So all the work that was going in was getting converted in work that was going out. And I thought that was absolutely insane. Obviously, the method in which they were measuring the efficiency was skewed in some fashion, because it's impossible to get 100% efficiency. The work in, work out just does not seem to, it doesn't make any sense to get 100%, because you remember you're producing thermal energy, you're producing heat, and the delivery of heat out into the atmosphere removes energy from your system. So the work that's being put in via combustion engine is being kicked back out, as entering the atmosphere. So I was like, well, the only way you're going to achieve 100% efficiency is if this engine was covered in nothing but skillets and you're frying eggs or something all the entire time. You were using every last bit of energy that's being produced. And it just doesn't happen. It's impossible. So, I mean, we didn't argue about it because I was just going to let him talk about his 100% efficiency engine, and I was just going to say, violating the laws of thermodynamics. Anyway, general definition for efficiency. Work out divided by work in, work out divided by heat put in. This is our thermal definition. This is our mechanical definition of efficiency. Does that make sense? And that's the second law of thermodynamics. I guess one more thing I should talk about really quick is heat death. So every time you're transforming one form of energy to another form of energy, there's usually the production of heat that's involved. Take kinetic potential energy to kinetic energy. Take chemical potential energy to kinetic energy. So chemical potential energy is the energy that's stored molecularly into an object. Gasoline has a great amount of chemical potential energy. So you ignite that gasoline, it releases all this energy. Well, most of that energy is not most of it. All of it's changed into this thermal energy. Okay, there's some which is kinetic energy. But it's heating up other objects. It's expanding out there. So very little of that energy that's in that gasoline is being kicked into work. Most of it is actually leaving our system, heating up the air around us, giving us this particle motion. That particle motion then is like kicking out radiation into space. I mean, the Earth is a pretty hot object. Not as hot as the sun, mind you, but it's always kicking out this radiation. It has a thermal signature. Okay? So, you're losing energy to the universe. When you talk about nuclear reactions, you're talking about converting matter into energy. That energy then is being released into the system. Well, we only absorb so much of that energy. The rest of it's getting kicked out into the atmosphere. That atmosphere is then kicking it out into space. So, when we talk about it, eventually the entire universe is going to be nothing more than thermal energy. It take billions upon billions upon billions upon billions upon billions upon billions of years for that to happen. I mean, every piece of matter eventually, well, not every piece of matter, but most of it's just going to be nothing. Well, yeah, about every piece of matter. It's all going to be gone, and we're going to be left with nothing more than a few particles that are vibrating, and that's going to be the thermal energy of the universe. You know, it's all going to be dissipated into the vastness of space. So, when we talk about the word heat death, that's what we're referring to. So the basically the general destruction of the universe. Everything is gone. It's no longer useful. Okay? So, you know, I won't be around. You won't be around. More than likely, your descendants probably won't be around. At least they won't remember you as being part of their lineage. I mean, but it's going to eventually happen. We're all going to just kind of fade away. Okay? Cool. So that's second law of thermodynamics, and that's the discussion on efficiency. The last law of thermodynamics, third law, is up next.